The video today is going to cover information pertaining to functions. So we're going to go through three objectives or topics that work with functions here. Our first one is identifying a function and its definition. Our second objective we're going to be covering is the domain and range with functions and equations and graphs and tables and things like that. And then our third topic is going to be function notation, how we use it and what it looks like, and the ways we can solve for values with that. So our first one we're going to be going through is identifying a function and defining a function. So we have our definition right down here, which we're going to be filling in here shortly. So our definition of a function. A function is a correspondence that matches each input value with exactly one output value. So that means for every x value that I have, which is generally what we're going to be using as our input value, I'm going to have only one output value that goes along with it. Now there's a big difference between saying I can have repeated numbers as an output value, but I can't have repeated numbers as an input value. Again, there's a uniqueness that goes along with this by saying for each input, there is exactly one output value. This means that we can have repeating output values showing up in a problem or a graph or a table of points, but I can only have one input value or each input value having its own one output that goes along with it. So let's take a look at a couple examples we have down here and see what this actually looks like in practice. So taking a look at 1a, b, and c. Number one, going to be a function, yes or no. And looking at it, this is going to be a function, yes. You might be looking at this, maybe a better circle here. You might be looking at this and thinking, well, hold on, I have two values showing up here for y, and y is the output value. And yes, I do have two output values that are the same here, but going back to our definition of a function, each input value has exactly one output value. So each input is exactly one output. So an input value of 1 has an output of 6. I have one input and it has one output. I have an input of 3 and an output of 6. But again, this one input has exactly one output. I don't care if the outputs retreat at all, or not retreat, repeat is all. So these output values could all be the exact same. They could be completely different. It doesn't matter. All I'm looking for is that I have one input value with exactly one output value, whatever that thing is. Let's take a look at number two. Number two, a function by our definition that we have up above. And no, 1b is not a function by our definition. I'm seeing here that I have an input value of -3 showing up twice. And along with that, the same input value has two output values. By our definition of something being a function, this table does not represent a function. And therefore, we'd be saying, no, this isn't a function here. Now we're looking at 1c, and we can start to see some of these different functions showing up in very non-conventional forms. So for instance, our example that we have here, I'm using players from the NFL team, the LA Rams, during the 2023 season. So we have some of the players, last names listed here, and then the positions that they are playing here as well. Just giving you an idea of some of these non-conventional and kind of unorthodox functions and questions we might be asked as they relate to functions and our definitions of them. So looking at this table, Does this represent a function? Yes or no? And yes, this one does. We're looking at this again by our core definition. Every single input here has exactly one output value here. Again, I have an instance where I have repeated outputs showing up, but that's okay because I have one output or one input corresponding with exactly one output. So outputs can repeat. That's perfectly okay. Inputs cannot repeat. We don't want any of that. That's where issues show up in terms of defining something as a function. So always come back to this definition that we have up here if you are asked to determine if something is or is not a function. Now let's take a look at some bit more mathematical ones and some graphs that go along with this as well. So looking at number 2, does number 2, the graph that's given to us there, does that represent a function? Yes or no? And yes, this one does. For every single x value that we have for every x value, we have exactly one output that corresponds with it. And we can see that as we go along the entirety of this thing. I have one x value with one y value showing up along this. And no repeating or double y values showing up at all. So yes, our first one is a function. Now let's look at number 3. Is number 3 a function by our definition? And no, it is not. So let's take an example here and look at an x value of 2. So we use the red dot here for this. So at x value, an input value of 2. What's the y value or the output value that corresponds with that? Well, if I look at my graph, I'm noticing I have a point up here and I have a point down here, meaning that this x value has 2 y values, or this input value has 2 output values. So by our definition of a function, this graph does not represent a function. Now we absolutely can have graphs showing up like this. There's nothing wrong with them. It's just that these graphs do not fit our definition of what it means to be a function. Remember, we always go back to that definition at the very top of our page as necessary to determine if something is or isn't a function. We do also have another way that we can go through and think on these things, and this works particularly well when we are working with graphs or given some kind of a graph or a visual to go along with these things. We have that thing that's called a vertical line test. And it tells us a graph represents a function if it is impossible to have any vertical line intersect the graph at more than one point. Now I think a best way to visualize this is to take a ruler or some kind of a vertical edge that you have. And we're going to take this, we're going to work with example 2 first, and I'm going to move this ruler from left to right along this graph. As I'm doing that, I'm checking to see, do I touch the graph at more than one point? And as I go left to right, I'm not doing that at all. So that corresponds with graph 2 still being a function. So we're good there. Let's take a look at number 3. If I start right at that vertex there, that point, and I notice right there, cool, it meets the vertical line test, it passes that, it's good to go. But as soon as I move just to the right of that, I'm now touching the graph in 2 points. I see as I move farther along to the right with that, I touch it at 2 points the rest of the way out there. So the vertical line test is an all or nothing test. If we are using a ruler in that vertical line and something on the graph fails the vertical line test at least once, then the entire graph is considered to not be a function. And that's why we entered that in as a no. So the vertical line test that we have here is very, very handy when we've been given graphs. But it's an all or nothing test. If it fails once, then the entire graph is not a function. If it works for the entire graph, then the whole graph is a function. Our second objective that we're going to take a look at this section is the domain and range of a function or a table of points or some information that's been given to us. So we're starting off with our definitions, like we did with our previous objective. The domain is the set of all possible input values of a function. Now I am going to note that there is a different way that this is sometimes described. So it's sometimes described as the input values or the independent values. So I'm listing both of those. Actually, we'll do this, so I'm not blocking anything there. There we go. So set of all possible input or independent values of a function. Now, we know that we have input and output values, so if domain is the input, then that would stand to reason. The range is the set of all possible output values of a function. And just like the domain, there are two ways that you can see these values described. Sometimes it's referred to as output values, and sometimes described as dependent values. So you could see it written either way. Again, we're normally used to seeing it as input and output, but sometimes some textbooks and online resources will have it listed as independent and dependent values as well. So just want to list both of those so you're aware of the two ways that it can be seen. But it means the same thing. So let's take a look at a couple examples that we have here with how we determine what the domain and range is and how we list that out. So looking at example 4, we're working with the domain. So we are asked to list all possible input values for the function that we've been given. And looking at number 4 here, we've been given a table of points for x and y values. Now again, domain corresponds with our input values, and generally speaking, we're going to be using x as our input values here. So in listing this out for ourselves, we would want to say the list of possible x values, or the domain, is going to be equal to, and we're using the curly brackets here, and then we're just going to list the numbers in this table top down exactly as they've been given to us. So the possible x values that we could be using with this, or our input values, are -1, 0, 1, 2, and 3. Similarly, with our range, we're looking at our y values, or our output values here. We're just going to be listing those off. Same way we did, using the curly bracket here. You might be noticing, well, hold on, I've got 6 showing up twice here with my output values. If you see one number repeating in the table of points you've been given or anything like that, you do not need to list it twice. You can just list it once, and that's perfectly acceptable there. And again, we're going to list this top down that's been given to us here in that column. That's going to be 8, 7, 6, 5. Now there are some textbooks and some programs that might want you to list those things smallest to largest, or in a particular order within the context of what that problem is looking for. So just be sure you're reading the directions and answering what they are specifically asking you to do. But by and large, we just list those in the order that we've been given if it's listed in a table like this. Taking a look at number 5, again, we're looking at the domain and the range. Make sure you're just specifying for yourself which one you are working with so you are looking for the correct things. So we'll start with domain again. So domain is having me look for x values. And we have been given some ordered pairs here, some points that can be on graphs. And again, if I'm working with the domain, I'm only going to be listing the x values or the input values here. Now with these ones, I'm going to list them in the order that they've been given to me. You can do that as 0, 1, -3, and 5. And I've also seen some people say, well, I like to list them from smallest to largest, like we did with example 4, and you're welcome to do that too. So all we'd be doing is just reordering them, smallest to largest values there. The range, which is the output values, the y values that we've been given, we're following the exact same pattern, except we're just looking at the y values in those ordered pairs. So if we listed those off just in the order they've been given to us, we're just going left to right there. So we'd have -2, 4, and then 3. We have an extra 4 showing up in there, so 4 shows up twice. We do not need to list it both times. We can just list it once, and that's fine. And again, just for the sake of showing it, you can list this from smallest to largest if you'd like to as well. Most places list it in that way, in that order, so we're just going to follow suit with that. Okay. Now let's take a look at number 6 here. Now we have some ordered pairs written in a slightly different format. So we're given these points on actual graphs themselves. So we need to, 1, identify the points, and then 2, determine the domain and range from there. When you're doing this, you aren't necessarily required to fill in and label what each of these points are, but it can sometimes be useful to write that out for ourselves. So I'm going to do that here just for the sake of making it clear what our input and output values are. And then we'll list our domain and range. So our first point that we have, that's going to be at -3, 0. That's right here. Our next point that we have, it looks like it's at 0, -1. That's here. And our last point looks like it's at 2, 2. That's right here. Now, listing our domain, again, I'm working with the input values, so the x values here. And I'm just listing those off. In this case, we're just going to go smallest to largest. So -3, 0, and 2. Looking for our range, I'm looking at the output values, the y values. And again, I'm just going to list those ones off, smallest to largest. And there we have our domain and range for number 6. Now number 7, 8, and 9 are where we start to look at these in graphs, and we have them as a list of points here. So all of these parts in the line are all individual points that we have on a graph. So now we're going to be listing and trying to find the domain and range with these. Now the tricky part with this is there are so many points that are along here that if you wanted to list every single one of them out, we wouldn't have enough space and time to be able to do that. So we're going to start using what we did in our previous classes, which is using interval and inequality notation to list the possible input values and the possible output values. So inequality notation and interval notation are the main ones that we use for that. We'll start with our domain. Actually, we'll do it slightly different here because we're using those other ones. So what I personally find very helpful is first identify which of these you're working with. So we're going to work with the domain. Now the domain is the input values or the x values that we have here. So we do not care how vertical this thing does or does not get. All we are looking for is the left and right kind of horizontal x values that show up with this thing. So I've seen some students in the past use this technique of essentially making a box around the graph and then determining their domain and range from that. So you can try that. I'm going to do this here a little bit just to show you what they mean. So if we're working with the domain, I'm only interested in the x values or the horizontal values here. So I'm going to list, put a little dot here. There's my leftmost x value, and then it goes all the way over to here. And I have an open circle, and there's my largest x value. So if we're going to list this thing using interval notation, we would list the lowest value on the left, so that'd be -1, largest value on the right, it's a +4. And now we need to fill in brackets or parentheses on either side of this interval. So can I include this -1 as an x value on this graph? And we can. We have a closed circle here, and a closed circle means we include those values. So we're going to put a bracket on the end. Looking at the 4, the largest x value, am I going to be including that? No, I'm not, because on the graph I have an open circle there. So that means I'm going to get a parenthesis on the end. So this is writing out the domain using interval notation. You can also list this using inequality notation, which is to say that I'm going to have an x value that's greater than something and less than something. So in this case, I have x is greater than or equal to -1, and that equal sign is in there, that little line below is in there because I have a closed circle here. And x is also less than 4 because I have an open circle showing up here. So I can't be equal to 4, but I can be any value that's less than that. And there we have our domain for number 7. After we have our domain, we're going to work with and try and find our range. So let's make a little box. I think that's a little helpful to see the vertical components that go along with this. So again, I'm only looking vertically because I'm working with the range here. So let's make a little box here. So our lowest x value is there. It goes all the way up to here. I'm referencing my lowest y value and my highest y value up there. So what is our lowest y value going to be, our lowest output value? Well, that looks like it's going to be 1. And the largest output value, y value, is going to be 4. Oops. Glitch there? There it goes. Now, can I include 1 in that range of things? Yeah, I can. I'm looking at this graph and I'm seeing that there is no open circle showing up at that lowest value, meaning that 1 is on the graph, and therefore I can include it in my range of values that I can use. Same idea with 4. At the largest and greatest value that we have there, there's no open circle, which means I can include 4 in the range as well. So now we have the range written in interval notation. Let's write it out again in inequality notation just to see the two ways that we can write this out for ourselves. So we have x is greater than or equal to 1, and x is less than or equal to 4. And so those are two ways of writing out the domain for number 7. Scrolling down here, let's take a look at number 8 and number 9. Kind of our two weirder ones, but still want to take a look at them and get those nailed down for ourselves. So we're going to use the same thinking we did in number 7, which is looking at these things horizontally and vertically depending on what we're working with. So let's start with our domain. So domain corresponds with our x values, so I'm looking at the horizontal values and x values, or input values, that we can use with this. So our input values are going to correspond with our x values here. Now again, similar to what we did with number 7, let's make a little bit of a box for ourselves. At least I think that's helpful as a visual with this thing. So horizontally, what are the x values that I'm using? Well, if I look at the ends of this graph, we've got arrows on the end. Now that tells us that we can assume that this graph is going to follow that exact same pattern forever, which means this thing is going to go forever in either direction with our x values. So we could think, well, what's our lowest x value going to be? If we continued going more and more negative with that, what's that going to become? Well, the lowest x value that we could get to would be -infinity, theoretically. What about in the positive direction? What's the largest thing we could get to? Well, that would be positive infinity. So if we think on that, that basically tells us we can use any x value that we want, or all x values are going to be used here. So the way we depict using all real numbers, or we can write that out for ourselves, using this little kind of a double R showing up here. You can also write this out as all real numbers. I'm going to just put num in there because I'm running out of space at the very end there, but all real numbers. Now let's look at our range. Again, we're thinking to what's our lowest input value, what's our lowest output value, I should say, and our largest output value. And again, we're looking vertically for our range. So I'm going to make a little bit of a box here. And I'm noticing, okay, the lowest x value, lowest y value, I should say, is there. And then it seems to go up like that forever. So what would our lowest y value be? Well, it looks like it's going to be -1, 2, 3. And then what about our largest y value? Well, again, the arrows on the end suggest that this thing is going to follow that trend going vertically forever. So this thing has a maximum value of infinity. And now we need to list, for interval notation, is the -3 going to have a bracket or a parenthesis next to it? And because this -3 is an actual point on the graph, there's no open circle there, I can put a bracket around it. For infinity or negative infinity, it doesn't matter which one it is always going to have a parenthesis around it because we can never actually reach infinity or negative infinity. So there we go. We have our range listed in interval notation. If you wanted to write it out using inequality notation, I'm just going to put that right below. We would just list this as a y value that is greater than or equal to -3. Because that assumes that we are going to be going on to y values all the way up to positive infinity there. So let's take a look at number 9 now, our last one. We're going to start with the domain again. Now I'm looking at this thing again with domain for my x values or my input values, so I am only looking horizontally with this thing. And again, I'm noticing like number 8, I have arrows pointing the very ends of this thing. Now that tells me that we can safely assume that this thing is going to go on in that same trend and pattern like it currently is forever. Which tells me that for the domain, I'm going to once again have all real numbers as my possible input value, or for all real values for inputs. I should be able to write the whole thing in here. There we go. Whoops. There it is. So our domain for number 9 is all real numbers. Now what about the range? Again, the range is looking for vertical values here. And I'm looking at this graph, and once again, I'm seeing the little arrows at the end suggesting that this thing is going to go up forever, and this thing is going to go down forever. So based on that, that tells me that my range is also going to be all real numbers. So we can use that double R. We can actually write out all real numbers. I'd recommend using the double sign, only because we're going to be seeing that more frequently with answers and answer keys and different online resources as well. But here's our examples and summary of the domain and range with functions. Our third and final objective or topic that we're going to cover with function notation, or just functions in general, is function notation. So function notation is the form that we are going to start to see more and more functions written in. It has a, I don't know, maybe slightly advanced look to it at first, but it is one that we are going to see more often. It does help us with organizing our thoughts a little bit more when we get to more advanced topics and equations and formulas that we're working with. So the main one I want to highlight is this expression right here we have written out. That right there is function notation. And we read that specifically as f of x. Or you can say the value of f at x. Two ways of saying the exact same thing. The more common one that we see, though, is this f of x way of stating it. So that's the one you're going to be hearing a lot more often. So in this case, the letter f names the function. So I have the function f here. And the variable x represents an input value from the domain. Way you can think of this as the input value is inside of the set of parentheses that we have right here. It's a silly little mnemonic device that, for me, it helps it make sense, but you can use it if you'd like to. So continuing on, we're told the notation f of x represents a specific output value corresponding to x. The other letters and names are G, H, J, K, etc., and so on. So what I really want to do here is take a slight second off the side. I want to write this in to show what this looks like, what we've seen previously, and what it's going to mean moving forward. So up until now, we are used to seeing ordered pairs, like for points on a graph, written in parentheses. We have the input value listed first, the output value listed second. And up until now, we have commonly seen that listed as an x value and then a y value. But now, since we have function notation showing up, we have some other ways that this can be written, we are now going to start see this written out as x and f of x. And we are not limited to just having x and y and x and f of x showing up. We can absolutely have a whole bunch of different variables showing up in here. So we could have t, we could have h of t. Maybe we have something where an equation tells us the height of something, the height of something based on the time that something's in the air. Maybe we have something like the variable, let's say h, and let's say p of h. And maybe in this scenario, p represents pay for h hours worked on a shift, or over a week, or over a month, or something like that. But I do want to really make it clear that we have all of these correspond to being our input values. And all of these correspond to being output values. So we're not going to just see y written in anymore. It's this whole f of x is an output value, h of t is an output value, p of h is an output value. So when you are looking at some of these numbers that we are going to be given in examples we're going through, always come back to, have I been given an input value or have I been given an output value? Or conversely, you could say, what thing do I not have? Do I not have an input value or do I not have an output value? Because we have to be given one and we're going to be solving for the other. And that's what we're going to see in our examples showing up here. So keeping that in mind, let's go back and take a look at some of these other problems that are listed in here. So take a look at problems here. Now another part that's really great about our function notation is we now have 4 different functions, all represented in different ways, and they're labeled now. So we don't have to guess at, is it this y, is it this y, is it this y, is it this y? Because up till now we've only used y as our output variable. Now we have other ones. So looking at number 10, question down here, we're told to evaluate f of 2. Okay, so 2 corresponds with a little bit of a quiz here. Is it an input value or is it an output value? And it's going to be an input value. It is inside a set of parentheses, so it is an input value. Now you have a couple ways you can do this. My recommendation is a calculator to help you out with it. But take one line to write it out for yourself. So I'm using the function f of x, and wherever an x shows up, I'm replacing that with a 2 inside a set of parentheses. And I can then enter all of that into my calculator, and I'm getting that f of 2 is going to equal -8. You can use a calculator to do that off the side on your own there. So great, there we have f of 2. We were given an input variable, or input value, find the output value. Looking at number 11, told to find g of 2. So 2 in this case is also an input value. It's inside of a set of parentheses. So we need to find which one of these corresponds with g of x. So here we go. So we're looking at this table here. Now we notice we've not been given any kind of an equation, so we can't do what we did with number 10, which is plug something in and then calculate a value from there. Instead, we have been given this table of points. Now, with number 11, 2 corresponds with an input value, so that means I have been given x, and I've been given x specifically to be 2. So what is the output value, the thing that I'm missing that corresponds with that? 0. So in this case, what is g of 2? Well, g of 2 is just 0. There we go. No extra work needed. Let's take a look at 12. We're working with h of 2. So h is going to correspond with our graph that we have right here. And again, I'm looking at this and noticing 2 is an input value, so it's an x value here. So I'm going to go find where that is on the graph. It looks like 2 is going to be right there as my input value. What's the corresponding output value that goes along with it? Well, output corresponds with y, so I'm going to be going up until I get right to where the graph is. And it looks like it's going to be right there. It's a reasonable approximation with that. So what is h of 2? Well, as an output value, it looks like 6. And there we have our answer. No real calculations necessary. We're just finding it on the table or finding it on the graph and getting to our answer. Looking at number 13, down here, told to evaluate j of 4. Now again, in this instance, 4 corresponds with an input value. So I'm using this table right here. I'm finding where is 4 in my input values. It's right here. So what's the corresponding output value? 3. So I can write in my answer, j of 4 is equal to 3. No extra work necessary. Looking at 14, it has h of 5. I'm getting ahead of myself there. So I'm going back up to my graph up here. I'm finding where is 5 on my x value. So I'm going over 1, 2, 3, 4, 5. So 5 is starting here. And then what's the corresponding y value that goes along with that? It looks like it's going to be 1, 2, 3-ish. 3, 3.5, something right around there. So we're going to list our answer for this one. I think the graph is ever so slightly off, and I believe the answer key is meant to be 3 in there, or negative 3 in there. But we would have a much cleaner looking graph, and you'll be seeing ones that are much nicer than these showing up on the examples or the ones in the homework or on tests. But that's our same way of going through, or our process of going through and getting to that. And looking at number 15, we're back to f of negative 4. So that's one where I'm coming up to my points, or my equation that was given to me, and I'm plugging negative 4 into that equation. So I have f of negative 4, substituting negative 4 in. And then off to the side, I'm using a calculator. I'm getting that f of negative 4, f of negative 4 is equal to 22. So there we have our answers for 10 through 15. Now looking at 16 and 17 on this page, we're told to find the value of x for j of x equals negative 7. So we're looking at our j equation. We're told to find the value of x, meaning I am trying to find an input value. So that means this negative 7 has to be an output value. I'm going to zoom this out a little bit so we can get everything in the same page there. There we go. So I'm looking at the table that I have right here. Negative 7 is an output value, so I found the output value there. What's the corresponding input value? 0. So my answer for 16 is x equals 0. And similarly, with number 17, we've got that graph again with its weird values showing up, but we're going to be working with that again. We have told to find the value of x for which h of x is equal to 1. So again, I'm finding x, that's an input value, which means 1 has to be an output value. So coming up to my graph, I'm finding where's the output value of 1. That's going to be right about there. So where's that corresponding input value going to be? Looks like it's right at a positive 4 there. So we list our final answer for that one as x equals 4. And that's everything that we have for this page here. Our last part with using function notation is to use it to help us graph linear functions. And really we're going to be using it for any kind of graphing that we need, but specifically for this we're using it for linear functions. So in our first example that we have here, number 18, we've been given the function f of x equals negative x plus 2. And we're told to evaluate f of x when the input value is 0, 1, and 4. Now again, it's very important with this. We need to identify what number have we been given and does it correspond with an input or an output value. After that, we are then just plugging that in for the input value or the output value. So for f of 0, 0 is an input value, so I'm going to be plugging that in as negative 0 plus 2, which is going to give me an answer of 2. For 1, I'm plugging in 1 into the equation. Negative 1 plus 2 is going to give me 1. And 4, also an input value, plugging that in for x in the equation. And simplifying that down, I'm getting a negative 2 as my answer there. Now, it has us off to the side here, it's asking us to write things out as an ordered pair. So remember, an ordered pair always has an input value and then an output value listed. So for the first point, that's going to be 0, 2. The second point, that's going to be 1, 1. And the third point, it's going to be 4, 2. Oops. 4, 2. There we go. And now we're asked to graph that line. Fix up this parenthesis here a little bit. So I now have 3 points. I can plot them on this graph and connect them all together. So our first point at 0, 2, right there. Second point at 1, 1. And our last point at 4, oops, should probably write it incorrectly, at 4, negative 2. 2 down there. And then we'd take a ruler and connect these things together as best we possibly can. Nope, I counted wrong. It should be at 4, negative 2. Going out 1, 2, 3, 4. Negative 2. There we go. And we'll get these things lined up as best we possibly can, roughly speaking. And then we'll connect those together, and hopefully it won't glitch on me. There's our graph. There we go. So let's do the same thing then with number 19. So again, we've been given input values of 3, 0, and negative 3. So I'm writing out my equation with those plugged in each instance. And you're welcome to solve this using a calculator or anything else at your disposal. But when we go through this, for this first one, we're going to be getting f of 3 is 0. For our second one, we're doing the same thing. We're plugging in 0 to our equation. And we're getting an output value of negative 2. And same thing for our last one. Plugging in negative 3. And we're getting an output value of negative 4. So our ordered pairs, again, rewriting each of these so they're ready to be graphed. We have the pair 3, 0. At the second point, 0, negative 2. And the third point of negative 3, comma, negative 4. And now we go through and we're going to graph each of these one by one on the graph that we've been given. So let's see, so 3, 0, that's going to be starting at the origin, 1, 2, 3, 0, right there. 0, negative 2, so put it down there, and then negative 3, negative 4, 1, 2, 3, 4, we have that. We'll bring out our ruler, let's adjust this thing, get it reasonably close. And there we have our graph. So we can use these, again, function notation to help us go through and graph these linear equations and eventually later equations that we've been given, remember to always come back to the idea of, have I been given an input value or an output value? And last but not least, a little bit of review from our previous class. The functions that we have been given here are in the form of y equals mx plus b, which we refer to as the slope intercept. Oops, it'll let me write. There it goes. The slope intercept form of a line. A little bit of a review there from our last class. But with that, that is everything that we have. What we'll be working with functions, function notation, domain and range, and our definition of functions as a generality for this class.